and welcome to BEaTS Research Radio, a podcast and YouTube channel dedicated to communicating science to the community. My name is Tuba B, and I'll be your host on today's episode with our special guest, Dr. Caroline Ménard. Dr. Caroline Ménard is currently an assistant professor in the Department of Psychiatry and Neurosciences at the Faculty of Medicine in the CERVO LAB at Laval University, where she investigates the root causes of brain diseases. Dr. Ménard is the holder of the Sentinel North Research Chair in the Neurobiology of Stress and Resilience. She was a postdoctoral fellow in the Center for Effective Neuroscience at the Fishberg Department of Neuroscience and Friedman Brain Institute, Econ School of Medicine at Mount Sinai, New York, for 3 years, where she led projects investigating the neurobiology of stress vulnerability and resilience and the development of mood disorders. Dr. Ménard has also previously investigated the neurobiology of learning and memory, diet-induced brain plasticity, aging, and Alzheimer's disease at the University of Montreal Douglas Hospital Research Center, which is affiliated with McGill University and the University of Quebec. Thank you so much for joining us, Dr. Ménard.
Thank you for the invitation.
Yeah. So we have a few questions prepared for today. To begin our interview, I was wondering if you could explain to us some of the current research efforts underway at your lab.
Yes, so my lab is really interested into learning the biology of stress response as well as resilience. We do use animal models, so mice, to understand the biology. But one thing that's really important to us is we also collaborate with clinician and brain or blood bank to verify what we find in mice, if it's also relevant for the human condition. So we are interested mostly in depression, but we think our research could be applied to all mood disorders, so bipolar disorder, anxiety, etc.
Oh, that is certainly interesting. On to my next question. There are medications available today to treat various mood disorders, including anxiety and depression, but scientists lack biological measurements that can accurately diagnose stress in the same way that we measure cancer or heart disease. Could you briefly explain how your team is working on a biological measure that can potentially allow health professionals to establish a diagnostic test on such mental health conditions?
Yes, so basically it's like a bit the holy grail of psychiatry to be able to find some biomarker that will really inform on diagnosis and help with the choice of treatment. And then so there's been a lot of effort in the last decade or so, I will say, to think outside the brain or outside the box, which is the brain, and then look at maybe what's going on in the blood, like inflammation, for example. There's been a high interest in the neuroimmune mechanism of depression because we're more and more seeing stress response and mood disorder as more a whole biology approach or whole body response instead of just the brain ruling everything. And so maybe we could find something in the blood that's different related to inflammation, for example, that could really help guide some treatment choice or diagnosis. So in my lab, we are also interested into the vasculature, so the blood vessel and vascular health. So we do combine different assays that will look at what's going on in the brain, what's going on in the blood, including inflammation, as well as vascular health and response. So we have this barrier that's protecting our brain, the blood-brain barrier. And what we found in our animal model is that it's more fragile or more vulnerable following stress, especially in animals who become depressed or have depression-like behavior. And so we're trying to understand why and the biology behind it, as well as what's protecting resilience or promoting resilience. And we found some biomarker that could be promising. So we are now verifying that. We did verify a few of them in human sample, and we are now looking for larger cohort to be able to validate this in like thousands of people.
Yeah, so essentially you are trying to find biological markers to detect the mental health conditions.
Yes, so our overarching hypothesis, I will say, is that vascular health could contribute to mental health status. And if we promote vascular health and blood-brain barrier integrity, so we protect our brain, maybe it could be a good way to be happier. But also it could also help develop new therapies and new drugs that will protect, because there's a lot of people who respond poorly or are going to be resistant to the actual treatment. And we think we could maybe bonify this treatment, but not only treating the brain, but also treating the body, including vascular health.
Wow. My next question is, your investigations show that chronic stress is associated with the blood-brain barrier, and you mentioned that as well, I think, briefly. So could you please explain your findings on how resilience or vulnerability to stress impacts the establishment of major depressive disorder symptoms?
Yeah, so what this is based on the work you mentioned I did in New York. So when I joined the lab of Scott Russo in New York, they did publish this study where they showed that change in the immune response in the periphery, so in the body, not the brain, but the body, could be modulated to promote resilience to stress or promote susceptibility in animal model. And one thing that's very intriguing is that the people who are not responding well to the current treatment we have often have inflammation in their blood that's higher than the general population. So we think this inflammation may contribute to the depressive symptoms. And then with the mice, we're trying to figure why and how it works. And so my question was, okay, the immune system is in the periphery in the body. How does it communicate with the brain? And then we have this barrier that's basically the frontier in between. So this barrier is very important for two things. It's going to feed, it's going to carry the nutrient from the blood into the brain. So the neurons are very big consumer of energy. So they need to be fed a lot. And so the barrier is going to play a major role into that. But also it's going to protect the brain from anything that's toxic or everything that's going to be deleterious that's circulating in the blood, such as inflammation. So it's acting a bit like a fence, and it's really going to protect our brain. One thing we found is when we subject the mice to chronic stress, especially a social stress, then it's going to make the barrier a bit more fragile, like I mentioned earlier. And the way it works is we have these little doors between the cell that form the barriers, and these doors will become open. So we're going to have a leakiness of the barrier. And this allows some inflammatory mediator circulating in the blood to reach the brain. And then this is eventually going to change the neuron activities and then the behavior. But one thing that's really important is what we found is that the region affected, it's not everywhere in the brain. In the male mice, it was the nucleus accumbens, which is a brain region important for reward as well as mood regulation. But then when I opened my lab in Quebec City, we were curious what's going on in female, because depression is twice more prevalent in women. So we think it's really imperative to study both sexes and gender. And then what we found is the region affected where the blood-brain barrier is leaky, it's different in female mice. So instead of the nucleus accumbens, in the female, it was the prefrontal cortex, which is important for anxiety, self-esteem, etc. So different behavior. And again, we try to confirm that in human tissue. So we're fortunate enough, we have access to a post-mortem human brain. So this is done with Douglas Bell Canada Brain Bank in Montreal, again, affiliated with McGill. And these are a brain that, unfortunately, the individual die by suicide, and either themselves or their family donate generously the brain. And so we can do some slices and look at the barrier in those human brain. And we confirm the sex-specific effects. So we confirm that in human depression, in men, it seems to be the accumbens, the barrier is leaky, and in women, it's more the prefrontal cortex.
I see. That I was actually going to specifically ask about that. So you just mentioned that depression, women and men differ in experience. Could you explain some of the differences you specifically observed in the lab and some of the conclusions it led you to, including your findings on depression biomarkers?
Yep. So I should say first that we do not recruit participants ourselves in the lab. So we really do more like animal work. But like I mentioned at the beginning, we do collaborate with clinicians or for example, here in Quebec, my lab is at the CERVO Brain Research Center. So we do, it's a part of a mental health hospital. So we do have projects with participants. In Montreal, McGill, the Douglas would be a good place to look at if people are interested. And then they have, like I mentioned, this major brain bank there. And why we think it's important to, again, consider women's health is, yes, the depression is twice more prevalent, but in line with what we found in mice, the symptoms are also different. So it's not black and white, it's more a spectrum. You need, I'm not a clinician, but if I remember well, you need to have, there's 9 clinical symptoms associated with major depressive disorder, so depression. You need 5 of them for over 2 weeks, more than 2 weeks, to be having a diagnosis of depression. And those can include different things. So anhedonia, which is the loss of pleasure, fatigue, you could have the loss of appetites, you could have anxiety. So there's like different symptoms that are associated with depression. And we see that anxiety is more on the woman side, versus in men, it's going to be change in the reward system. So for example, behavior that would be related to, for example, more risky risk-taking behavior, or like, for example, over abusing of alcohol, or I don't know, those kind of like risk-taking behavior. And then the self-esteem also can be in more women, but men will have more anger. So you have these like sex differences, which is why we think it's interesting and important to investigate different brain region that might play a role in these symptoms. And finally, the treatment is also different. So some class of antidepressant, I have to say that we do have antidepressant that work, and then some class of antidepressant work better in men than in women. But the thing with antidepressant is kind of a mystery box. We give them, but it's we give them and we cross our finger and we hope it's going to work. But often some people will have to try sometimes 2, 3, 4 different antidepressants before finding the right recipe for them. So that's why we think having biomarker that could help choice of treatment will be really helpful.
Um, and in a past interview, you mentioned that around 30 to 50% of these people respond poorly to current antidepressants, which mainly target neurons. Could you explain maybe some of the causes for this resistance that you briefly mentioned?
That's a great question. So that we're actually asking money for it to try to figure how antidepressant affect the barrier that's protecting our brain, and if some antidepressant work better than other. So far, it's kind of unknown the biology behind it. But yeah, so basically, the way it works is if you have a diagnosis of depression, depending if you're a man or a woman and what type of symptom you have, the doctor is going to prescribe to you one type of antidepressant, but often it's going to take 6, 8 weeks before you see an actual effect on the symptoms. And if you are super depressed, or you have, for example, suicidal ideation, you want to be helped as fast as possible. You don't want to wait for too long. So there is some hope. So there's been some novel antidepressant that have been developed in the past few years. So it's a very exciting time in psychiatry. I think people should be hopeful. And then, so there's been some novel fast-acting antidepressant that have been developed, such as ketamine, for example, but you need to have it in a clinical set. So you cannot just have it at home. You have to go in the clinics to have it. So that's why we're trying to better understand how these molecules work. And by better understanding the biology, then we can try to design drugs that will be more effective and will help everybody. And yeah, so having tools to guide the choice would be also really helpful. But yes, this is basically the end point that we're aiming. So everybody could have a treatment that work for them and work as fast as possible.
Yes. And lastly, moving forward, what are some of the next steps your lab plans to focus on? And do you think mental health disorders such as anxiety and depression are likely to be completely prevented in the future?
That's an excellent question. So there's 2 things my lab is aiming to do. So first, so far, when we study the biology of the barrier, we always look at endothelial cell, which is the first line of defense, I should say. But there is other cell type that are behind, so astrocyte, pericyte, that make the connection with the neurons. So we now have project working on that, so to better understand the communication between the cell and how they carry the signal to the neuron. We're also trying to understand how the antidepressant affect the barrier, like I mentioned. But one thing we also test are preventive strategies. So can we use physical exercise or diet that could protect our barrier and then promote stress resilience? So we know physical exercise, for example, it's known to improve vascular health. So maybe it could protect the barrier. But how does it work? What is the biology behind it? So what we do is we purchase mice wheels. So the mice have access to wheels during the stress exposure, and then so they can run during the night as much as they want. They run, it's really impressive. They can run up to 10, 15 kilometer a night. So, and it's a 24, 25 gram animal. So it puts all of us to shame. But yeah, basically, so, and if the mice that run the most, are they the one that become resilient, or like we're trying to see how it will work at the biological level. But this is something that we're trying to work on. So yes, a strategy to develop novel therapies, but also preventive strategy, which we think is really important. And in all these experiments, we always consider sex, so both male and female. And then when we're going to confirm in human sample, always including men and women. We think it's very, very important, because women's health has been a bit forgotten in research throughout the decades. And one thing that I want to say also is that we often think as cardiovascular disease or heart disease as being men's disease, but it's not true. It's the main cause of premature death in women, stroke and heart disease. So that's why we think it's really important. And as far as resilience, first, stress is not always bad. So stress is bad when it's chronic and you don't have control over it. So it's like lasting for a long time and you feel like you have no control. But stress can be also good. So it helps us develop coping strategy when we're better prepared when we face adversity the next time. But if you feel like you're stressed, you need to find your recipe for resilience. So can be like I developed some baking skills during the COVID pandemic. Could be like doing some gardening. Physical exercise is really good because your head, like it empty your head. Sometimes you just need to take a 15 minutes in your day and think about yourself. But it's very important. That's why we study what we see in the resilient mice. It's not like being an on-stress control. There's a lot of adaptation, not only in the strategy to face stress, but also at the biological level. So I was trying to understand resilience, because we think we could also find novel strategy or mechanism that could be helpful to develop drug that will promote resilience.
Sounds good. So, essentially, building our resilience is one of the best, one of the most effective ways to prevent mental health diseases.
So we think resilience, it's personal. Like people will have different recipe of resilience. Unfortunately, there's not one magic solution that will apply to all. But yes, it's important to try to keep control of the stress. So if you feel like you're overwhelmed and it's becoming a burden, you need to seek help. It can be like psychotherapy, and at some point when it's too much, taking some antidepressant, and then to come back to a level where you can control everything. But yeah, my take-home message would be to not hesitate to ask for help, but also try to figure some resilient strategy. So when you feel stressed, have like a little plan to what you should do or you could do to help yourself, and also talk to each other. It's really important to talk, to ask if people around you are okay, and listen to what they have to say.
Thank you so much, Dr. Ménard, for joining us today. And thank you to all the BEaTS listeners for your time. Don't forget to like and subscribe to our YouTube, Twitter, and Instagram channels at BEaTS Research. BEaTS Research Radio is supported by the Ottawa Heart Institute and the University of Ottawa.